In this work, we have investigated several aspects of pattern formation in a monolayer of granular particles subject to vertical vibration. This is a collaboration between people from 3 different institutions in Madrid, Spain, and Bayreuth in Germany. The experimental setup is quite standard and has in fact been used by several groups over the years. We have a circular horizontal cavity which is vibrated vertically using a commercial shaker. The cavity has 14 centimeters in diameter, and the shaker oscillates with a frequency of about 80 Hz. Particles are steel cylinders, and these cylinders can move in the vertical direction. There is an upper lid that closes the cavity on the top and leaves a small free vertical space so that particles move but cannot overlap. Particles collide and as a result they can move and diffuse in the horizontal directions. So particles can explore the available space or the available area and can form patterns in the steady state. The initial configuration is obtained by hand, which is a hard process because we are dealing with really dense packings of particles using fractions of area covered by particles between 70 and 75%. This is a typical initial configuration with particles located with random orientations and positions. This picture corresponds to the azeotropic phase. These are the particles, but we have also calculated the tetratic order parameter using colors to represent the value of this order parameter. In this phase, the azeotropic phase, the order parameter has a very low value. But in the steady state, particles arrange in the so-called tetratic phase, and the order parameter on each particle is high. In this phase, particles are oriented on average along 2 equivalent directions, which are perpendicular to each other. In this picture, these directions are clearly seen. They point along the diagonals of the slide, more or less. Also, there are regions where particles form layers, and also at the circular boundary, particles sometimes are oriented perpendicular to the boundary instead of in the planar direction, which is more standard or more common. One interesting thing is the presence of 4 defects, which are revealed by the presence of 4 regions where the order parameter is depleted. So we can see the defects located at the corners of a square. These defects, so to speak, restore the symmetry of the tetratic phase, which is disrupted or broken by the circular geometry of the cavity boundary. These are the locations of the 4 defects. This video shows the time evolution from the initial configuration. The system gets more ordered with time, and in the steady state we can see the tetratic state with the 4 defects. The defects move and fluctuate, and in the paper we analyze these fluctuations. Also, it is interesting to know that this behavior is identical to the one shown by Monte Carlo simulations of a similar system. So it is remarkable that the behavior of a granular system, which is a non-equilibrium system, is quite similar to the behavior of an equilibrium thermal system. In fact, in our work we have discovered additional similarities which are explained in more detail in the paper.